Okay, so I think we are good to record here. Alright, so what was I saying beforehand? Right, so we determined the number of protons and neutrons. So all that's left is determining the number of electrons. So we look at that by at the charge of the phosphorus there. Since it's -3, we know that the number of electrons is going to be 3 more than phosphorus in its normal state. So phosphorus, normally in its ground state, the number of electrons and protons is equal. So since it normally has 15 protons, that would normally mean in its ground state it would also have 15 electrons. But since it's in a 3- state, that means it has 3 more than normal. So it has 15 plus 3, so then that would mean it has 18 electrons. So in this case, 15 protons, 16 neutrons, 18 electrons. That would mean our answer would be B. So does that one make sense to everyone? Awesome. Alright, so on to question 2. So what is the atomic mass of 12C? So the atomic mass is determined by usually the number up top here. So atomic mass units is essentially just another way of kind of stating up here. It's sort of equivalent to grams per mole in most instances, but not quite. So in this case, the 12 just indicates that it will be 12 atomic mass units. So there's nothing too crazy to that question. And then next one here is, what is the atomic mass of an element if 4 grams of it contains 2.98 times 10 to the 22nd atoms? So in this one here, the key thing to note is that it's giving you a number of atoms. So remember that I said that AMU is similar to grams per mole. So we can figure out the mass in atomic mass units by looking that they give us 4 grams of it and they give us how many atoms there are. So if we remember, if we want to determine something in grams per mole, we have 4.00 grams, which is the mass of our sample. And then in order to determine how many moles we have, we need to multiply the number of atoms by Avogadro's number. So if you remember that, we'll take our 2.98 times 10 to the 22nd atoms and then multiply it by Avogadro's number. So remember, unit cancellations, we want the stuff we're getting rid of on the bottom. So Avogadro's number is 6.022 times 10 to the 23rd atoms per mole. 1 mole. So then atoms will cancel. And then we will be left with grams per mole, which is roughly equivalent to AMU. So then if you type that through, well, I guess we won't actually need the calculator in this instance, Grace, so that's handy. So then you would get your answer of 80.8 grams per mole, or 80.8 atomic mass units. So then your answer would be B. Ooh, fun one. So malprotoline has the following mass composition. So it has 86.59% carbon, 8.35% hydrogen, and 5.05% nitrogen. So the empirical formula of malprotoline is. So one way I always loved to visualize these questions is, since they give us percentages and they don't actually give us like the mass of the sample, I like to imagine that we have 100 grams of whatever this molecule is. So in this instance here, if we have 100 grams of this random molecule, then just understanding that since these are percentages, we will have 86.59 grams of carbon, and then we'll also have 8.35 grams of hydrogen, and then 5.05 grams of nitrogen. So if we look at the options on the left here, these are all in terms of molar quantities, right? So if these are in grams, we want to convert these to moles. So what we can do is pull the masses from the table. So 86.59 grams for carbon here. So carbon will have an atomic mass of 12.011 grams per 1 mole. And then we'll see that grams cancels, and then what would that equal, Grace?
Just doing that now. Okay, so 86.59 divided by 12.011. That equals 7.209.
7.209.
I don't know. Do you want more decimal points?
No, I think that should be fine.
Perfect.
So then we'll likewise want to do the same thing for these other two. So 8.35 grams. And then hydrogen has a mass per 1 mole of 1.008 grams per mole.
And that equals 8.2837.
2837.
I don't know.
Yeah, close enough. We're not being super particular about sig figs right now. And then next we do the same for nitrogen. So that's 5.05 grams. And then, and what's nitrogen again? Is that 14.01?
Yep, 14.01. And then that equals 0.3605.
3605. So, now that we've determined the molar quantities, what I like to do to visualize it is I like to write out the formula. So we have C with a subscript of 7.209, with an H with a subscript of 8.2837, with an N with a subscript of 0.3605. So the next thing you want to do is you divide each of these by the smallest number. So in this case, it's going to be the nitrogen, the 0.3605. So ideally, this should get you to whole numbers. So this one divided by this one will just get you to an N of 1. And then you essentially want to do it for the carbon and the hydrogen as well.
Right.
So what does that look like, Grace?
Okay, so if you take the carbon, which is 7.209 divided by 0.3605, that equals very, very close to 20.
Yeah.
19.997.
19.997. Well, that's enough within the range of rounding it to 20.
Yep. And then the 8.2837 divided by 0.3605 is 22.978. So that's close enough to 23.
And then the nitrogen is just divided by itself.
1.
So that's just 1. So then this would be your empirical formula right here. So then that would give you your answer of B.
Perfect.
I apparently overestimated how many blank slides I would need to solve these. Okay, so choose the incorrect formula or name formula combination. So looking at our first one here, this is iron something oxide. So remember, in the case of iron, that can have a charge of +2 or +3. So you need to specify what that is. So just looking at this guy here, we're going to have 3 oxygens, and oxygen always has a charge of -2. So that's going to bring a total charge of -6. So in order to balance that out, we need the irons to have an overall charge of +6. So if there's 2 of them, that must mean that the iron is +3. So the charge is correct in that case. And since it's an oxygen, we just list it as oxide. So that one is correctly named. This second one, sulfurous acid, that's just one of the ones you would have had to memorize. So that one is also correctly named. Another one you might confuse that for is sulfuric acid, but that's essentially just, you have to go over your naming conventions and know how to name those. But thankfully for you guys this year, since you have access to tables, that should be a lot easier.
Yep.
And then this one here, this is just knowing the names of some complex ions. So NH4 is ammonium, so that's correct. And then ClO3 would be your chlorate ion. So this one would also be correctly named. This one here is calcium, so calcium is always +2. You don't really need to specify charge on that one. And then H2, so hydrogen like that would be called hydride, so calcium hydride is correct. Where this one is incorrect here is silicon is kind of a transition element, so this would like to follow the molecular naming conventions. So in this case, where the big issue is they don't specify the number of oxygens. So in this case, the correct name, since there's 2 oxygens, would actually be silicon dioxide. So that's why this one is incorrectly named. Okay, so given the following reactions, Fe plus Br2 goes to iron bromide, and then iron bromide plus an additional bromine goes to that fun looking thing. So if each reaction gives an 82% yield, what mass of Fe3Br8 is produced from 1 gram of iron, assuming Br2 is in excess? This is essentially a theoretical yield calculation that you do twice. So first thing we want to do is figure out how many grams of FeBr2 we can get from 1 gram of Fe. But in order to do that, we will need the mass of this guy. So that's easy enough. We can just pull that from the periodic table. This guy we're going to have to calculate. So FeBr2. So what are the masses of those, Grace?
All of a sudden the cloud went over, so now I can't see. Here, pull it down. Just a second. So iron has a molecular mass of 55.845 grams per mole.
Grams per mole.
And then bromine is 79.904 grams per mole.
904 grams per mole. And then we have
So
2 of those, so that gives us...
So 2 times 79.904 plus the 55.845 gives us a grand total of 215.653 grams per mole for the iron bromide salt there.
I always forget how heavy bromine is in comparison to everything else.
I know. It's heavier than iron. Isn't that crazy?
Yeah, so if we want to figure out our theoretical yield for this guy here, we'll start with our grams of iron. So we have 1 gram of iron. And then we want to convert that to moles of iron. So in order to do that, we will use the atomic mass of iron. So that is 55.845 grams per 1 mole. And then we will want to convert that to moles of FeBr2. So in that case, I guess we wouldn't really have had to calculate that mass. Oh well. So
I guess not, but
yeah. So it'll be 1 mole to 1 mole. So then this will give us moles of FeBr2. So what would that be?
so that equals 0.0179
79 moles.
moles.
So the question said that each reaction gives an 82% yield. So this is our theoretical yield, but it's saying in actuality we're only going to get 82% of that. So in order to calculate that, we'll just multiply that 0.0179 moles by 0.82 as a percentage, which will give us the actual yield for the first reaction.
Which is 0.01468.
1468 moles. So now this number is what we're going to use to determine the yield for the second one. So this guy here, I guess we are actually going to have to calculate the atomic mass of Fe3Br8 in this case. Oh well. So we're going to have 3 times 55.845 grams per mole plus
8.
8. Goodness. Times
I know, right?
79.
79.
It's like a miniature protein type mass almost.
Yeah, 806.
Jeez.
0.767.
806.767 grams per mole.
Hefty.
So, now we can calculate how many grams we're supposed to get. So, if we started with 0.01486 moles of FeBr2, and then looking at the molar ratios in the reaction here, for every 1 mole of Fe3, Fe3Br8, we have 3 moles of FeBr2. That will convert us to moles of Fe3Br8, and then multiply that by our grams, so that would be 806.767 grams per 1 mole. And then that gives us, what would that answer be, Grace?
What was the molar mass? 807?
806.767. Sorry, I'm just running out of room on the slide there.
No, that's okay. I get 30. Oh, wait a second. This is wrong. 806.
You have to divide it by 3 there also, just remember.
Yes, I get, okay, 3.948.
3.
Which is incorrect, apparently. Oh, wait, did we multiply this by...
We haven't multiplied it by the
the 82?
Yeah.
Oh, okay.
So this is our theoretical yield for the second reaction. But remember it said that every reaction had an 82% yield. So in order to determine the actual yield, we'll just multiply that by 0.82 for 82%. And then
Which gives us 3.237 or 3.24.
Yeah, so 3.23.
Close enough, yeah.
We were playing fast and loose with the sig figs there, so it's probably just a difference in rounding. So that would be your answer. So determine the mass percent of hydrogen in NH4Cl. So to do a mass percentage question, you essentially want to figure out the mass of hydrogen over the mass of the total molecule. So that's going to involve some calculating molar masses. So mass of molecule. So in order to calculate it here, you want to figure out the mass of hydrogen compared to the mass of the entire molecule. So for hydrogen, we have 4 hydrogens in this total molecule here, and every hydrogen has a mass of 1.008 grams per mole. So that's going to equal roughly 4 divided by the mass of this entire molecule added up. So we're also going to have our 4 times 1.008 grams per mole for the hydrogen, plus our mass for the 1 nitrogen atom, so that would be 14.01 grams per mole, plus the mass of the chlorine, which is chlorine 35.45.
That's right.
Yes. Okay, so 35.45 grams per mole. So then this all added up would be your bottom. So then you just take your top 4 divided by that, and that would give your ratio, and that would be what, Grace?
That gives 4.032 divided by 53.495. And then dividing those two gives 0.0754. And then you have to multiply that by 100 to get your percent, which gives you 7.5.
7.5%. Which thus means the answer would be B. So nothing too crazy with that one. So which statement below is true? So A, metals gain electrons to have a positive charge. So remember, this one is incorrect because in order to get a positive charge, you want to lose electrons because electrons have a negative charge. So that one is false. The second one here, metals gain electrons to have a negative charge. So remember that in general, metals always like to have a positive charge. So the negative part is the issue with B. So C is correct here in that metals lose electrons to have a positive charge. So that's essentially just correcting the errors in the first two here. The reason D is incorrect is nonmetals always lose electrons to have a positive charge. So in general, not always, nonmetals usually like to have a negative charge. So for example, like oxygen is 2-. So in most cases that they like to have a negative charge. So that's why D is incorrect. And transition metals can gain 2 or more electrons to become metal ions. So remember that transition metals are similar in that they want to lose electrons to become ions. So they won't ever gain electrons. So that's why C is correct, whereas A, B, D, and E are incorrect. So number 9, how much chlorine in grams is required to produce 12 grams of CCl4 according to the following reaction, assuming that methane gas is in excess? So this looks balanced already. So this is going to be another math type of question. So just looking here, they give us 12 grams of CCl4, so that's what we want to produce. So we need to determine how much Cl2 we need. So just looking here, we're grams. We're going to be hopping onto this reaction, so we're going to convert to moles of this, and we're going to also convert to moles of that. So first thing I think we should do is let's calculate the atomic mass of these two guys here. So the Cl2 is just going to be 35.45 times 2. So that should be...
Oh, sorry, I did the other one first. 35.45 times 2? 70.9. Yeah.
Grams per mole. And then what would the CCl4 be?
153.81.
81 grams per mole. So one thing I kind of I should point out as like a question solving technique I like to use is I call it a roadmap essentially, which is I like to just look at what we're starting with and figure out what steps I need to do to get to where we want. So the final thing we're looking for is they want the grams of Cl2, so that will be our final step of Cl2. And then the number we start with is grams of CCl4, so that's the left side of our roadmap. Cl4. So in order to get from the left side to the right side, the first thing we want to do is we want to figure out how to get this into moles, because then we can hop along this reaction here. So then we can figure out a way to get from grams of CCl4 to moles of CCl4. And then, now that we have moles of CCl4, now that we're on the reaction, we can readily convert from moles of one to moles of another. So we can then go from moles of CCl4 to moles of Cl2. And then once we have moles of Cl2, that's easy enough to convert back to grams of Cl2 once we know the mass, which we just calculated. So we just want to chain these calculations together. So we have 12 grams of CCl4. And then in order to convert that to moles of CCl4, we'll use the mass. So that was 153.81 grams per 1 mole. So grams cancel there. So now looking at our molar ratios, we want to get rid of moles of CCl4. So that would be 1 mole of CCl4 divided by 4 moles of Cl2. And then now we are in moles of Cl2. So then we want to convert to grams of Cl2. So in order to do that, we use our other atomic mass. 70.9 grams per 1 mole. And then this mole will cancel with this mole. This guy cancels with this guy. And then we will be left with an answer in grams of Cl2, which should be 22.1, assuming I did the numbers correctly here.
Yep, that's what I got.
All right, excellent.
Perfect.
I really put a lot of blank slides here. Oh well. So what is the answer with the correct number of significant figures in the following calculation? So, in order to determine the correct number of significant figures, you need to remember your rules for adding, subtracting, multiplying, and dividing significant figures. So with adding and subtracting, it's the number of decimal places that determines where your significant figures are stopped. So in this case here, looking at this fraction, we want to figure out this top part here. So when you're adding numbers with significant figures, the number with the least amount of decimal places determines the amount of decimal places in the new answer. So if we look here, this guy has 3 decimal places, this guy has just 1, and then this guy has 4. So then that means we'll just add these together, and since this guy only has 1 decimal place, the new number can only therefore also have 1 decimal place. So what would that be, Grace?
So adding 75.032 and 2.3.
Yeah.
Like, do you do these one at a time? I think so.
Yeah, you want to...
Okay.
When they ask these specific, like, sig fig questions, you just do it step by step, keeping the amount of sig figs rules in mind for every operation, and then that carries forward.
Gotcha. Okay, so then the first 2 numbers would be 77.3.
That's what the 0.0046 added?
No, I just did the 2 first ones.
Okay. Yeah, sure. Let's do that. So you said, what was that?
77.3.
77.3 plus 0.0046. So in this case, the addition rules also apply, so you just want to keep 1 decimal place when you add these 2.
Right, and then that'll give you the same thing,
Yeah.
77.3.
Divided by 10.2. So now the rules that apply when you're dividing or multiplying is that the number with the least amount of significant figures determines how many significant figures your answer can have. So thankfully with this guy here, our top number has 3 sig figs, and our bottom number also has 3 sig figs. So we don't have to do any trimming of significant figures, so you'd essentially just punch that through, and then you would get your answer of 7.58.
Yeah, so this one gives 7.578, but then remember that you have to round up that 7.
Yeah. So you asked if the bottom had 5 sig figs, you would still use, yes, exactly. So if, for example, you had like, say, 77.2 over 22.687 something or other, this one has the least significant figure, so then your answer would have 3 sig figs. Likewise, if you're multiplying and one just had 3 and one had like 10, you would just use 3. So it's always dependent upon which number has the least amount of significant figures in it.
Perfect.
Okay, so titanium 4 oxide is produced in the action by sulfuric acid on that fun thing. So in the reaction, 8 times 10 to the 3 kilograms of iron titanium trioxide yielded 3.67 times 10 to the 3 kilograms of TiO2. What is the percent yield of the reaction? My, that is a big number. Okay.
Good Lord, do we have to balance this?
Is it not balanced?
No, it looks like it is.
Okay. Goodness.
It just wasn't that obvious that it is, but yeah.
Had me stressed out there for a sec.
Same.
So, this presents us with a lot of information off the top, obviously, but I like to figure out a roadmap. So, they want the percent yield of the reaction. So, that is going to be our final part in our roadmap. And then the beginning part they give us is, they said this much yielded that much that. So this is our starting point here. Kilograms of FeTiO3. So, where's my pen there? So this would be kilograms of FeTiO3. So we want to figure out how to get from here to a percent yield. So the first thing we can do is we can convert that kilograms to grams of FeTiO3. Since dealing with kilograms of anything in chemistry is not fun. So that's just a simple unit conversion, so that'll be easy enough to do. And then once we're in grams of FeTiO3, we can convert that grams of FeTiO3 to moles of FeTiO3 using an atomic mass. So we can figure out that conversion. And then once we're in moles of FeTiO3, we can then go to moles of TiO2 using the reaction formula. And then once we have moles of TiO2, we can use a chemical formula to go to grams of TiO2. And then this here is our theoretical yield. So once we know the theoretical yield, and since they gave us an actual yield, we can use that to go to percent yield. So that is essentially going to be the roadmap we are going to follow here. So yeah, this one is going to have a lot of math in it, but if we stick to the roadmap we made, it should make sense overall. So, starting here, we have 8.00 times 10 to the 3 kilograms of that fun thing. And then in order to convert to grams, using our metric scale, we'll remember that per every 1 kilogram there is 1,000 grams. So then punching that through, your kilograms will cancel, and then that will give us...
Times 10 to the 3.
My scientific notation part of my brain is broken right now. What would that be?
8.00 times 10 to the 10 to the 6.
Okay. 0. Why did that get erased? Times 10 to the 6 grams.
Yep.
So that's our first part done here. Now we want to convert grams of FeTiO3 to moles of FeTiO3. But we're going to need a conversion factor. In this case, that's going to be the molar mass of that fun-looking thing. So, I'm going to need your help on this one, Grace. So, let's see.
Sure.
We have Fe,
Iron.
So,
Yeah,
what would that be?
So iron is 55.845.
845 plus 1 titanium.
Which is 47.867.
867.
And then you add 3 oxygens, which are about 16, or 15.9998 or something, 9994.
I do a lot of organic chemistry. It's just kind of burned out of my brain at this point.
Okay, so then 55.845 plus 47.867 plus 3 times 15.9994 gives us 151.7102 grams per mole.
102 grams per mole. Okay, so now that we have our conversion factor, we can go from grams of FeTiO3 to moles of FeTiO3. So, we said we had 8.00 times 10 to the 6 grams. And then, in order to convert that to moles, 151.7. What the heck just happened?
Oh boy.
151.7102 grams per 1 mole. And then that would be what, Grace?
So 8 million divided by 151.7102 equals, okay, 5.2732 times 10 to the 1, 2, 3. 4.
4.
So then you'd probably want to track your sig figs here.
Thankfully, it looks like they're just rounding the
Yeah.
3 sig figs, so we'll just kind of play fast and
Great.
loose with it right now.
Excellent.
So that's the second step done. So we are definitely going to need a second slide for this one, but squeezing this in here, just looking at the molar ratios, thankfully it's going to be 1 mole here to 1 mole here. So it's essentially multiplying and dividing by 1. So the amount of moles of titanium oxide is going to be the same as the amount of moles of iron titanium oxide. So that one is converted. So the next step is we want to go to moles of titanium oxide. So that number 5.2732 times 10 to the 4th moles.
So to do that, you're calculating the theoretical yield, right? But we're given how much they actually get.
Yeah.
And then you have to calculate the actual experimental yield. So do we have to convert, I guess, the theoretical, or do we have to find the theoretical yield?
Well, they want the percent yield, right? So they give us the actual yield, and the percent yield is the actual yield over the theoretical yield. So
right. Okay.
we're
Okay.
finding the
Good.
theoretical yield right now. And then once we know the theoretical yield, which in this case, in this roadmap, is the grams of TiO2, that gives us the percent yield.
Okay. Perfect. Yeah. Yeah. Was missing a step there.
So
Thanks,
this is,
Richard.
yeah, no worries. So this is our moles of TiO2. So in order to convert that to grams of TiO2, we'll need another unit conversion here. So we need to figure out the mass of this guy here. So titanium, what was that again?
Titanium is 47.867. And I think someone asked where we will be able to view the recording. I think we'll just post it to Discord, right?
That, or I might upload it to YouTube, or maybe I'll give it to Ellis, but I will keep you guys posted on where that gets put up.
Okay.
15.9994 for the 2 oxygens, so then that gives us the total mass of, what would that be, Grace?
So that is 47.867 plus 2 times 15.9994 equals 79.8658.
8658 grams per mole.
Grams per mole. Yep.
So then we will take that and use it as the unit conversion here. So 5.2732 times 10 to the 4 moles. And then we want grams on top. 79.8658 grams per 1 mole.
That equals, oh boy, 4.21148. That's a lot, but whatever. Times 10 to the 6.
Grams.
Yeah, grams.
So then, looking at our roadmap here, this is grams of TiO2. So now we want to use that and go to the percent yield. So they gave us our actual yield was 3.67 times 10 to the 3 kilograms. So actual yield was 3.67 times 10 to the 3 kilograms. And then I guess we are going to have to convert this grams back to kilograms for our theoretical yield. But that's no big deal. So in that case, it would be 4.21148 times 10 to the 6 grams. And then remembering our unit conversions, there's 1,000 grams per 1 kilogram. So then that would be 4.21148 times 10 to the 3, I believe.
Yeah, to the 3.
Yeah, kilograms. So then remembering that our formula for percent yield is our is equal to our actual divided by our theoretical. So in this case, we have our actual yield and our theoretical. So then we'll just punch those in. So we have 3.67 times 10 to the 3 divided by 4.21 times 10 to the 3.
And that gives you 0.87.
0.87. So if we want
71.
that as a 871. So if we want that as a percentage, you just multiply that by 100. So then that gives you 87.1%, which I believe is the correct answer. Yes, it is. So a lot of math on that one, but it definitely throws in a few useful topics altogether. So, question 12. To determine the molarity of a HCl solution, a 0.24 gram sample of Na2CO3 is titrated with 23.04 moles of HCl solution. What is the molarity of the HCl solution? Okay, so just looking at this here, they have not balanced the reaction. Oh, that's not fun. Okay. Well,
love that.
Our first step is we're going to have to balance this fun thing. So looking at the left side here, we have 2 sodiums, whereas on the right we only have 2. So I'm just going to put a 2 in front of the Na for now. Oh dear, whoops, 2. Oh, no problem there. So then we'll put so then we have 2 chlorines here. So then we will put a 2 in front of the HCl here. So then just looking, we have 2 chlorines, 2 chlorines, 2 sodiums, 2 sodiums, 1 carbon, 1 carbon, 3 oxygens, and 3 oxygens, 2 hydrogens, 2 hydrogens. So that would be the balanced reaction.
Woohoo!
Thankfully, it's not too bad. So we want to determine our final thing is big M, or moles per liter of HCl. So that's our final thing we want to find. And we're starting off with a sample of Na2CO3. So that would be grams of Na2CO3. So this is our starting point. We want to go to that. So from grams of Na2CO3, we can go to moles of Na2CO3. Because we want to always look at the reaction here. So once we're now on the reaction here, we can figure out how many moles of HCl we need. And then once we know the moles of HCl, we can then go to a concentration because we know the volume of liquid, which is 23.04. So from that, we can go to moles of HCl. So starting here, if we want to go of grams of Na2CO3 to moles of Na2CO3, we want to calculate another atomic mass for this fun thing. So
You're getting good at that.
yeah. So we have 2 sodiums at 22.989768 grams. I don't know why
Oh my God.
I don't know why I know so many decimal places for sodium, but plus 1
My
carbon.
periodic table doesn't even have that.
12.011 grams per mole, plus 3 oxygens at 15.9994. So yeah, you don't have to type in all those decimal places, but
I'm going to. 2 times 2, 2.98976.8. Oh boy. Plus 12.011 plus 3 times 15.9994. That's 105.9887.
9887. So now that we have that conversion ratio, we can go to moles of Na2CO3. So we have, what would they give us? So 0.2400 grams. And then go to moles, that is, put the grams on the bottom, 0.9887 grams per 1 mole.
Okay. So that is 0.00 226,439 moles.
Moles of Na2CO3. So then looking at our molar ratios here, for every 1 mole of Na2CO3, we have 2 moles of HCl. So we're essentially going to have to multiply that by 2. So that'd
Okay,
be...
so that times 2 equals 0.00452878 moles of HCl3.
Sorry, could you
Or sorry,
repeat that?
HCl. 0.00452878.
7, 8, that should be enough.
Yeah,
Moles
moles of
HCl.
HCl.
So now they want the molarity of the HCl solution, so that's defined as moles per liter. So they give us the mole, or so we've calculated the moles of HCl, but we don't have the liters yet. That is in milliliters, so we're going to have to also convert that, but that's not too bad. So 23.04 milliliters, and then remembering your conversions, there should be 1,000 milliliters for every 1 liter. So then that would give us
0.02304
liters. So if we take that
Perfect.
and then divide that by the moles for liters,
Perfect.
that will give us an
Then
answer
you get,
in moles per liter.
0.19656,
So
which then you will round to the answer at D. Perfect.
so then that would be your answer.
Perfect.
In which compound the oxidations... Oh, they missed. Okay. That tripped me up. In which compound is the oxidation state of carbon plus 4? Okay.
Oh, that's a terrible question. Oh,
So
Crazy.
looking at these, to determine the oxidation state of something, you just look at something that has a fairly consistent oxidation state, and you want to add it up to the overall charge of the molecule. So just looking at A here, we have 1 carbon, which we don't know, so 1 times C, which is our unknown, plus we have 2 oxygens, and oxygen, when it's in this, is always having a charge of -2. And then, since there's no charge on the molecule, it means our overall charge is going to be 0. So I like to represent it like this because it's essentially like a math equation and you're solving for an unknown. So then this 1 times C, we just have C plus 2 times -2, so that'd be -4. Whoops, just gotta get rid of that. -4 equals 0. So then you add 4 to both sides, so then you have C equals plus 4. So that would be the charge for the first one. So I don't think I'm going to do all of them, but I will do B as well, since that one has a more complicated thing. So in this case, we have CaCO3. So in this case, calcium is a group 2 metal. So those always have a charge in their ionic state of +2, and there's one of those, so we have 2 plus 1 carbon at our unknown charge, so we'll just put a C, plus 3 oxygens, and remember oxygen in that always has a charge of -2, and then there's no overall charge, so then that would be equal to 0. So then just simplifying this equation, we have 2 plus C minus 6 equals 0. And then just add these two, so then we have C minus 4 equals 0, and then we'd have C is equal to plus 4. So if you did it for all the other ones, you would find that the charge would be plus 4 in all those instances. So that's why the answer is E, all of the above.
perfect.
So a krypton gas in an 18.5 liter cylinder exerts a pressure of 11.2 atmospheres at 28.2 degrees Celsius. How many grams of krypton are present? So I added just that little bit of information there because that would come in handy. So remember, when we're dealing with gases, we want to use the ideal gas law. P. Oh wow, that is not a P. Okay. Gonna erase that. PV is equal to nRT. So the units of all this are going to depend on the question, but the R I always remember is 0.08206 liters times atmospheres per moles degree Kelvin. So you essentially want the units of your pressure, your volume, your moles, and your temperature to equal the units of your gas constant here. So looking here, we've got liters are correct for our volume, atmospheres are correct for our pressure. The one thing we do need to convert is to convert Celsius to Kelvin, but that's easy enough. So in order to convert Celsius to Kelvin, that's just your Celsius temperature plus 273.15. So that would give us 298.4?
301.35.
301.35. Okay. 301.35 Kelvin. So,
Yeah.
now that we have a pressure, a volume, we know R, it's a constant, and we have a temperature, we can calculate N, which is our moles of krypton in this case. And then they want krypton in gas, so once we know the moles, we can just use this conversion to go to grams. So plugging all that in, we want to isolate N in this equation, so we'll divide both sides by RT. So then we get N is equal to pressure times volume divided by R times temperature. So then we just fill in our variables now. So our pressure in this case we said was 11.2 atmospheres times our volume. We're in an 18.5 liter tank divided by our gas constant of 0.08206 times our temperature, which was 301.35 Kelvin. And then that would give us something in moles. And what would that be, Grace?
Just 1 second. 301.35 divided by 0.082058 equals 8.379 moles.
379 moles. So then we just want to convert that back to grams. So we have 8.379 moles. And then we have 83.798 grams.
98, whoops.
Which we just pulled that from the periodic table, so...
And then we get 702. Yep.
702 grams. Which would be our answer to the question. So that's easy enough. So... Number 15. Which gas occupies the largest volume at standard temperature and pressure? So this one, you can do it one of two ways. You can do it using just kind of inference with magnitudes of scale and masses, or you can actually calculate it out using math. But in a multiple choice exam, you ideally want to do it in as little time as possible, so we'll do it just kind of the intuitive way. So remember from the ideal gas law, PV is equal to nRT, that what N is doesn't matter. 1 mole of gas of any kind, whether it's hydrogen or some complex molecule, is going to occupy the same space if it's the same temperature and pressure. So what's going to change here is the number of moles of gas. So if we look at all of our options here, they give us these not in moles but in grams. So if we look at this intuitively, if one of these has the lightest molecular weight, then 2.5 grams of it would transfer to the most moles. So does that make sense? I feel like that might be confusing. Yeah. So essentially,
Okay.
yeah, if you have 2.5 grams of something with a very light molar weight, you'll have more moles of that compared to 2.5 grams of something with a heavy molar weight. So thankfully, in this instance, just by viewing it like that, yes, moles and volume and moles are proportional. So
Yeah.
we essentially don't need to actually figure out the exact number of moles. If we just look at the approximate kind of molecular weight of each one of these substances, the lightest one should give us the most moles, since all the masses of them are equivalent. So if we're just spitballing this here, this bottom one, D here, so carbon has 12, 2 oxygens are 16, so that'd be roughly 44 grams per mole. And then helium, if you pull that from the table, is 4-ish?
Yeah, 4.0026.
0026. And then chlorine, that one's going to be like
about
roughly 70.
76. Yeah.
And then hydrogen, that one's going to be about 2-ish grams per mole.
Great.
So just looking at these, hydrogen has the lightest weight, but it has an equal amount of mass. So therefore, it's going to have the most moles. So since hydrogen has the most moles, and since every mole, regardless of what gas it is, occupies a certain amount of volume, the 2.5 grams of hydrogen would therefore occupy the most volume. So just by doing that intuitively, we can actually figure that out without actually having to do all that much math. So does that make sense to everyone?
I think a couple people said it did before. But yeah, volume and moles are proportional. Yep. So at standard temperature and pressure, the P, R, and T will be equivalent. So then your volume will be equal to nRT over P. So the only thing that's different will be the number of moles.
I just know like inversely proportional and like causal things can sometimes be confusing. So I just want to make sure I'm not confusing anyone. But
For sure,
it looks
yeah.
like everyone gets it, so that's good. So
Awesome.
next question is, what is the total pressure if 1 gram of hydrogen and 5 grams of helium are mixed in a 5-liter flask at 20 degrees Celsius? Assume both species are ideal gases. So this one is dealing with both the ideal gas law, PV equals nRT, plus Dalton's law of partial pressures, which states that the total pressure of a system is equal to the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas, and on and on and on. So in this case, we can see that we are dealing with helium and hydrogen. So we only have to deal with 2 gases. So in order to figure out, they want the total pressure, we need to figure out how many moles we are dealing with in total of gas. So we have 2 of these in grams, so we're going to need to convert both of these to moles. So let's start with the helium. So we have 5.0 grams of helium. And then helium, what was the mass of that one again, Grace?
4.0026
6 grams per 1
per mole. And then that'll equal 1.2492
92
moles.
moles of helium. Okay, and then we'll do the next thing for hydrogen. So we have 1 gram of that guy. And then H2 would be 2 times 1.00794 grams. So then what would that be, Grace?
That's 0.4961 moles.
Moles of H2. So then, in the ideal gas law, the moles of gas doesn't matter which that is. So the total moles of gas in the system, we just add these 2 together.
Which gives 1.7453 moles total.
So now that we know the moles, we can plug this into our ideal gas law. So in this case, we want to figure out the pressure, so we'll isolate the pressure in the equation and divide both sides by V. So then we'll get pressure is equal to nRT divided by V. So then we'll just fill in our numbers. So our moles was 1.7453 times R, our gas constant, which is 0.08206 liters atmospheres per mole degree Kelvin, times our temperature. Oh, they gave it to us in Celsius.
That's okay. 273.15 plus 20,
Yeah,
293.
293.15 Kelvin.
Yep.
All divided by our volume of. Did they give us? Oh, yeah, 5 liters. And then.
Divide that by 5. That's okay. 8.3967. So 8.4.
Atmospheres. So yeah, that would be 8.4 atmospheres would be your answer for 16.
Yes.
Number 17. A 1 liter flask is filled with 0.16 grams of unknown gas at 743 millimeters of mercury and 25 degrees Celsius. Calculate the molar mass and identify the gas the unknown gas is. Ooh, that's fun. Okay. So just looking at the numbers they give us in terms of an ideal gas law, they give us a volume, they give us a pressure, and they give us a temperature. So looking in terms of PV equals nRT, we know all the other ones, so we can calculate the number of moles. So we'll start there. But unfortunately, we're going to have to do some fun unit conversions because they threw in some imperial stuff here with millimeters of mercury. So we want to convert that millimeters of mercury to atmospheres.
Okay.
So I believe you guys will be given a table of conversions, but the conversion for this is there's 1 atmosphere per 760 millimeters of mercury.
Yes.
So what would that be?
I should probably do that calculation. 743 divided by 760 equals 0.9776.
Atmospheres. And then 25 Celsius to convert that to Kelvin, that's just 298.15 Kelvin.
Yep.
Okay, so now we want to solve for n in our equation, so we'll divide both sides by RT. So then we will get n is equal to PV over RT. So then, plugging in our numbers here, we have our pressure of 0.9776 atmospheres times our volume, which they said was 1 liter, all over R, which is our gas constant, 0.08206, times our temperature is 298.15 Kelvin, and that will give us something in moles.
And I get 0.03995.
995 moles. So then if we want to go to grams, they said they gave us the amount of grams up here. So if we want to calculate grams per mole, we'll just take the number of grams we were given, 1.60 grams, divided by the number of moles.
1.6 divided by, I think I said that wrong before, 0.03996.
Oh, well.
Which equals 40, yeah.
Yeah.
Wait a second, did I do that right?
I
missed the decimal.
Like 4.
What the heck, I'm off by a factor of 10, so I must have messed up something. I think I did 0.0082058. Let me just try that again. Yeah. Yeah, I think that's it.
Okay, well, regardless, you should be getting roughly 4. Point.
Oh,
something.
Yeah, there we go. Yes, that's
grams
correct.
per.
And my moles were correct. I was punching in 1.6 like a dummy.
Oh, okay.
0.16. Okay. So then we know that helium has a molar mass of 4.0026. So very close to what we get.
Yeah. So then you would just look, realize that's on your table, and then the answer would be helium.
Yipper.
Okay, oxygen gas generated by the reaction is collected at 27 degrees Celsius and fills a 2-liter vessel at a pressure of, why did they do this? 750 torr. What is the
I don't
amount in
know.
moles of potassium chromate consumed in this reaction? Oh, this is an ugly one. Okay. So looking at what
All right.
we have to deal with here, we're starting with all these things, so we'll use our ideal gas law, and then going from that we can calculate the number of moles of our gas, so in this case that'd be O2, and then for moles of O2 we can go to moles of KClO3, and then from, oh no, we don't actually have to go to grams of KClO3. Okay, that's good.
Just in moles, yeah.
Oh, that's a little bit nicer. Okay. So, let's start by using our PV equals nRT. So just looking at our units here, our temperature, we're going to have to convert to Kelvin. So that's easy enough. Just add 273, so that should be 300.15
Yep.
Kelvin. Liters is good, and unfortunately we're dealing with another imperial unit here, so 750 torr. So torr is just another word for millimeters of mercury, so the unit conversion for that is 1 atmosphere per 760 torr.
So that equals 0.98684
68
atmospheres. Yeah.
So in order to figure out moles of O2 then, we'll just isolate N, divide both sides by RT, so N is equal to PV over RT. So then that equals our pressure, which we calculated as 0.9868 atmospheres, times our volume, which was 2 liters from the question, divided by our gas constant of 0.08206, times our temperature of 300.15 Kelvin. And then what would that be?
684. Sorry, I'm messing up. Times 2 divided by 0.08206 divided by 300.15. I get 0.0801 moles, which is not an answer.
Well, that's not the final step yet.
Oh, good.
Of,
Oh,
so this is in moles of O2 because that's the gas. So it's
Right.
wanting the amount in moles of KClO3 that was consumed. So now that we
Okay.
have moles of O2, we can use our reaction to go to moles of KClO3. So if we just look at our subscripts here, if we have 0.0801 moles of O2, and we want to get to moles of K2Cl3, so we want moles of O2 on the bottom to cancel, so that would be 3 moles of O2 divided by 2 moles of KClO3, and then that should give us our final answer.
yes. 0.0534.
Moles. And then that's our answer.
Perfect.
How much heat is required to warm 1.5 kilos of sand from 25 degrees to 100 degrees Celsius? Given the specific heat capacity of sand is 0.84 joules per gram degrees Celsius. So remember, questions like these, when you're dealing with heat, you want to use the formula Q, which is your heat, is equal to your mass times your heat capacity C times your change in temperature delta T. So just looking at what we have here, they give us a mass, they give us our heat capacity, and then they give us an initial temperature and a final temperature. So the only thing we're going to have to worry about here is we want these units to cancel, so the mass of sand is in kilograms, but the heat capacity's units of mass are grams. So we're going to want to convert the kilograms of sand to grams. So 1.5 kilograms. Then remember there's 1,000 grams per 1 kilogram. So then that would be 1,500 grams.
Yeah. 1500. Mm-hmm.
My mental math is not completely shot yet. So now we fill in our numbers. So our heat, Q, is equal to 1500 grams, which is the mass of our sand, times the heat capacity of 0.84 joules per gram degrees Celsius, times our delta T. So delta T, remember, is our temperature final minus our temperature initial. So in this case, our temperature final will be 100 degrees Celsius minus our initial temperature of 25 degrees Celsius. So then, essentially, if you plugged all that through your calculator, you should get an answer for Q in joules.
That's right, which is the answer there.
Yeah, times 10 to the 4 joules. So just doing a quick mental double check of your answer, you're heating up the sand, so it would make sense that your answer would be positive. Which I guess is not really helpful in this case, considering all the options that you can choose are positive, but it's just helpful double check.
Are all your guys' questions going to be multiple choice? Probably not. I would bet not.
I'm guessing they're going to have some, like, fill in the blanks, too.
Mm-hmm. That's interesting. Okay, sorry to interrupt.
Oh, no worries.
The midterms aren't... Oh, yeah. Yeah. That makes sense.
Gives me a chance to grab a drink of water. Okay. How much heat is released by the combustion of 177 milliliters of acetone, given the density of acetone is 0.788 grams per milliliters, and the heat of reaction is negative 1790 kilojoules per mole? Okay. So looking at our roadmap here, our final thing we want is something in kilojoules of heat. And what we start with is a volume of acetone. So we need to figure out how to get from the volume of acetone to kilojoules of heat. So one thing we can do is they gave us a density, so we can go from a volume of acetone to grams of acetone. And then once we know the grams, we can go to moles of acetone, because they gave us the chemical formula, so we can calculate a unit conversion for that. And then since we know the heat of reaction, we can go from moles of acetone to kilojoules of heat. Alright, so let's start with this. So they said we have 177 milliliters of acetone. And then they also gave us a density. So they said that the density was 0.788 grams per 1 milliliter. So what would that be in grams?
177 times 0.788 equals 139.476.
476 grams per... sorry, not grams per mole. That's just grams.
That's grams, yes.
So now we want to convert that to moles of S. Oh, they didn't give us the molecular mass. Oh, no. Okay.
Love that.
So we're going to have to calculate the formula mass for this guy. So we have 3 carbons times 12.011 grams per mole plus 6 hydrogens times 1.00794 grams per mole plus 1 oxygen at 15.9994 grams per mole.
The puppy outside is barking. That's 58.081.
0.081.
Yes.
Now we can go from grams of acetone to moles of acetone. So we'll take our, what was our grams? 139.476 grams per, it was, whoops, 58.081 grams per 1 mole. And that will give us something in moles of acetone.
Which gives 2.4014 moles. Close enough, yes.
So when you're dealing with a heat or reaction that has a negative sign, the way I like to visualize it is you can put that on the right side. So you can view it as when you react it, you start off with 1 mole of acetone plus 4 moles of oxygen gives you 3 moles of CO2 plus 3 moles of H2O plus negative 1790 kilojoules per mole of acetone. So you essentially can put it on the right side. So then you can essentially use that as a unit conversion to figure out how many kilojoules. Much in the same way you would if you were just converting between moles of something. So in this case, we figured out that we had 2.4014 moles of acetone. And according to our reaction stoichiometry, for every 1 mole of acetone, we generate negative, because it's exothermic, 1790 kilojoules of heat.
Which gives us negative 4.30 times 10 to the 3 kilojoules. So it actually gives 4,298.5, but then you have to round that to 3 sig figs. So that's 4.30
So then
times
that
10
would
to the
be
3.
A for number 20.
That's right. Yep.
Calculate the delta H of reaction for this reaction. So we did a similar example like this guy last week. So remember, with your sub-reactions, you have 2 options to try and get them to add up to the reaction at the top. Is you can either flip them, and that flips the sign of the delta H, or you can multiply them by some constant, which also multiplies the delta H by that constant. So, just looking at this first guy here, we've got an Fe2O3 on the right side, whereas in the parent reaction, it's on the left. So I think a good idea is let's flip this left one here, or the top one, sorry. So then if we flip that, that'll become Fe2O3 goes to 2Fe plus 3 halves O2, and then our delta H also gets flipped. So instead of being negative 824, it becomes positive 824. So then, looking at our second one here, there's a CO at the left-hand side, but there is a 3, whereas there's only a 1 in front of here. So I think it's a good idea. Let's multiply this whole thing by 3. So in that case, therefore, that becomes 3CO plus 1/2 times 3, so that'd be 3 halves O2 goes to 3CO2. And then our delta H, since we multiplied the whole thing by 3, also gets multiplied by 3. So 282.7 times 3. So then, just looking to make sure we crossed everything off, this 3 halves O2 up here cancels with this one. And then we're left with Fe2O3, which is on the top, plus 3CO, which is on the left-hand side, goes to 2Fe plus 3CO2. So that, our reactions now add up to the parent reaction, so that's good. So to determine the delta H, now we just sum the delta H's of all the sub-reactions with the changes we made to them. So in this case, we flipped the sign on this one, so now it's positive 824. And then this one we multiplied by 3, so that we just multiply that by 3, and then we add them together. And that gives us...
that gives the 23.9.
Yeah, so that'd be negative 23.9 kilojoules. So then that would give you the answer for this guy.
Yes.
A 31.1 gram block of pure gold with the heat capacity of that, initially at 69.3 degrees Celsius, is submerged into 64.2 grams of water at 27.8 degrees Celsius. What is the final temperature of both substances at thermal equilibrium? Oh, this is going to be a fun one. So,
No kidding.
when we're dealing with a question that's mixing a hot and cold object, the Q, or the heat of one object that's taking in, is going to be equal to the heat that the other object is giving off, so the negative Q. So if you remember, our Q equals MC delta T formula, in this case, we're going to be using a version of that for both of these. So what we need to do is figure out which one is our Q and which one is our negative Q. So just looking here, the hot object would be the gold, which is at 69.3, and the cold object is going to be the water. So the hot object is the negative Q, so this would be gold. And then our water is going to be our positive Q. So then we want to sub in MC delta T for both of these sides for each of the respective materials. So MC delta T of the water in this case, they gave us the mass of the water in the question as 64.2 grams times the specific heat capacity of water, which is 4.18 joules per gram degrees Celsius, times delta T, and then remember delta T is TF, our final temperature, minus our initial temperature. So TF, that's what we're trying to figure out. So I'm just going to label that X, because that's our unknown, minus gold's initial temperature, or sorry, minus water's initial temperature, which was 27.8 degrees Celsius. And then that is going to be equal to the negative of the heat that's being given off by the gold. So in this case, the mass for this one is 31.1 grams times the C value of gold, which was 0.128 joules per gram degrees Celsius, times our TF, which we are trying to figure out, so that's X, minus our initial temperature of 69.3 degrees Celsius. So now what you're essentially going to have to do is rearrange the equation and solve for X. So do you guys feel like you're comfortable rearranging an equation like this to solve for X, or would you like to see it in more detail? You're good? Okay.
Great.
So essentially, if you rearranged this equation and solved for X, this would just give you your final temperature TF, which would be equal to 28.4 degrees Celsius. So a great way that you can just quickly mentally double check the answer is when you're heating a hot and cold object, your temperature should ideally be between the hot and the cold temperature. Well, it has to be. So you want your answer somewhere between 27.8 and 69.3, so yes, that makes sense. And then another thing you want to double check is just looking at the specific heat capacities. Water has a heat capacity of 4.2 joules, whereas gold has like 0.128. So the gold doesn't actually hold that much heat, so it would make sense that the final temperature would be a lot closer to the cold object, which can absorb a lot of heat, compared to the hot object, which can't give off that much heat. So if you look here, this 28.4 is a lot closer to water's initial temperature compared to gold's initial temperature. So that just mentally makes sense why that would be the answer. So arrange the following atoms or elements in terms of decreasing first ionization energy from highest to lowest. So in terms of ionization energy, so ionization energy refers to the amount of energy that's required to remove an electron from an atom. So if you remember, metals love to lose electrons to become positive. So that makes sense that metals would have very low ionization energies because they readily want to give up the electrons anyway. Whereas if you have something that is very stable or wants to gain electrons, they are going to have very high ionization energies. So just looking at our options here, our two metals, which are going to be our candidates for the lowest ones, are potassium and magnesium. So they are this guy here and this guy here. So the main difference is they are going to be in different rows of the periodic table, and one is also a group 2 compared to a group 1. So in general, group 1 metals are easily ionizable. They're very reactive. Also, the potassium is a group lower, so the attraction between the protons on the inside of the atom to the outer shell electrons is going to be less. So that means potassium is going to be our lowest ionization energy. And then magnesium, because it's a metal and because it's higher, would be our second lowest. So that takes care of those. And then the next ones we want to deal with are phosphorus, sulfur, and fluorine. So that is this guy, sulfur, fluorine. So, just looking at these, ideally, with in terms of ionization energies, generally they decrease across a row. So, in this case, sulfur is going to have a higher first ionization energy because it is closer to looking like a noble gas, which they all want to, compared to phosphorus. So phosphorus would have an easier time going to the left, whereas sulfur would have a more difficult time doing it. So phosphorus would have a higher ionization energy than sulfur would. Or sorry, I mean sulfur would have a higher ionization energy than phosphorus would.
Yeah.
And then the last one here is fluorine. So that one's going to be the highest because it's near its top row here. So it is going to have a strong attraction between the protons in the nucleus and the electrons in the outer shell. How long it will be going until? Well, I'm planning on essentially going as long as you guys want.
Mm-hmm. I think so.
So, yeah, until, like, run out of questions or...
Yeah, maybe like, I don't know, 7. There's more than 40 questions.
Yeah, I think there's 42. Plus the
Let me
written
look.
answer.
Oh, yeah, plus 4 written answers. Yeah, 42 multiple choice plus B1 onto B4, I think. So 4 written ones. So I'm thinking, like, I don't know. As long as we have people here who still want to be here.
Yeah, like, this is for your guys' benefit, so... I had a question for earlier I was hoping to ask, so I'll try to be quick. Oh yeah, no worries.
Yeah, no problem.
It'll be a little bit. So, what was I saying? Right, fluorine is a halogen, so those really don't want to give up electrons. They really want to look like a noble gas by gaining an electron. So fluorine would therefore have your highest ionization energy. So your answer would be A in this case. So according to Hund's rule, which element is expected to contain unpaired electrons? So Hund's rule is essentially stating that electrons like to fill unoccupied orbitals one at a time, like this, before they start filling in the other ones. So, essentially what we want to do is look at the electron configuration of each of these guys in their highest orbital.
Ooh, baby. Okay.
So, where on earth is SR in the table? Oh, okay.
I know, I'm
38.
Practically. Oh, here we go. Yeah, it's
So 38, its highest
5S.
group is going to be the 5s. So remember that S only has the one suborbital. So that's going to fill in like that. So that one is all going to have paired electrons. So that's good. So then the next one is zinc. And oh boy, where's zinc? Okay. So that's a 3d10.
Yep.
So then the highest one there. So the d orbital has 5 subshells that look like this. So then we go 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10.
Yep.
So then germanium is our answer because germanium, its highest, is going to be the 4p orbital over here. But no.
What the heck is that? Oh, here. 32. Germanium. Yeah, it'd be,
Hang on. Oh dear, what just happened?
4p2.
Oh no, did I seriously go back to the beginning? Oh god.
Oh, no.
Hang on. Sorry folks, some minor technical difficulties here. Go,
That's
go.
4p. Yeah. Yes, 4p2.
Oh dear, what happened?
Struggling. Oh, go back.
Yeah, now we have to go back. I'm so lost. Okay. There we go. So sorry
There.
about that. So, germanium. Nope. Okay, there we go. Germanium is going to have the 4p2. So remember, the p orbital has 3 subshells. So germanium here is going to have 2 electrons. So Hund's rule says the first one goes in the first subshell, second one goes in the second subshell, and then there's no more. So these two are going to be unpaired. So the unpaired electrons would be germanium.
Perfect.
Okay. So which of the following atoms or ions is paramagnetic? So paramagnetic, remembered, essentially means that it has unpaired electrons, that it can be affected by a magnetic field. So we essentially need to look at these guys and figure out which of these have unpaired electrons. Oh boy, that's going to be fun. So I'm not going to do all 6 of them, but we can do a couple. So I say let's do sulfur and fluorine, since we haven't dealt with ions yet.
For sure.
So looking at our periodic table here, sulfur is going to be normally a 3p4 would be its highest. So 3p4, so that would look like this. So 1, 2, 3, 4. But the big difference here is sulfur also has 2 more electrons because it has a 2- charge. So 5, 6. So sulfur has all of its electrons paired. So therefore it is diamagnetic. So sulfur would not be one of them. So then if we look at the iron, iron in this case would be, where's that?
Oh boy. 3D 1, 2, 6.
3d6. So remember the d orbital has 5 subshells. 4, 5. So normally it's 1, 2, 3, 4, 5, 6. So that would have unpaired electrons already, but it's plus 3, so that means we took away 3, so we take that 1, 2, 3. So I'll have 3 unpaired electrons here. So therefore, that one would be paramagnetic. So if you did all of them, you would see that sodium, boron, and iron 3+ would all be paramagnetic. Which of the following statements is correct with respect to the as yet unknown element with the atomic number 119? So the correct answer is it will be a member of the alkali metal group. So this is essentially just looking at the names of groups in the table. So we have 118 here, so 119 is going to wrap around in the table and be right here. So that's going to be part of the alkali metal group, which is the group 1 metals such as lithium, sodium, potassium. So looking at the other ones, it'll be a noble gas. So the noble gases are these guys right here. So that's not true. And then, yeah, so that's your answer there. Okay, 27. A possible set of quantum numbers for the last electron added to complete the electron configuration of an atom of selenium in its ground state is. Ooh, boy.
Okay.
Where's
Selenium.
Selenium is 34.
34.
So
Was
the
not looking
full-
there.
The full electron configuration for that guy is going to be 1s2. So how?
2s2.
So I feel like this is going to be a helpful thing to point out while we're here. So in order, how you count electron configurations going down the table is you essentially look at each group here. So I'm assuming everyone can see my laser pointer. So helium should be on this left-hand side here. So you start at the top left of the table and you essentially work down to where your element is. So we start, there's two 1s elements. So we go one, oh, this is going to be hard with both a laser pointer and a pen. Hang on. So we go 1s2, and then we jump down a row. So then we are dealing with the second row here. So then we have 2s2. And then we hop over. There's no D's here. So then we have, this is the p orbital right here. We have 6 of them. 1, 2, 3, 4, 5, 6. So then 2s2, 2p6. So then we write that down as part of our electron configuration. Where is my pen? 2s2, 2p6. And then you hop down another row doing the same thing. There's no D's yet. So then we go 3s2. 3p6. And then here is where it gets fun. So now we're dealing with a d orbital. So we go 4s2. The d orbital, in this case, you actually subtract 1 instead of its row. So it'd be 4s2, 3d10, and then to get to selenium, it is 4p1, 2, 3, 4. So then that would give us our full list. So 3p6, 4s2, 3d10, 4p4. Our main point of concern is going to be our 4p4.
Great.
So then looking at our quantum numbers, remember that for our quantum numbers we have n, l, ml, and ms. So each of these kind of have specific values that they're allowed to be. So n essentially kind of refers to what shell or row of the table we're dealing with. So we know that the highest energy electrons are going to be in the 4p4. So the n refers to the row, so in that case that's the 4. So we know that n in the highest energy would be 4. So remember that L refers to what specific orbital we're dealing with. So in this case, that refers to the p orbital. So each of these has kind of a number corresponding to it. So 0 represents the s orbital, 1 represents the p orbital, 2 represents the d orbital, and 3 represents the f orbital. So we know that since we're dealing with the p orbital, L must be 1. And then ML corresponds to which subshell of the orbital we're dealing with. So remember that P has 3 subshells. So how you number those is ML can go from negative L to positive L. Or in this case, it can be negative 1, 0, or 1. And each of those correspond to the shells. And then MS corresponds to the electron spin, so that is always positive 1/2 or negative 1/2. So essentially we want to look at our options here and determine which one is valid. So looking at our n equals 4, that automatically crosses out B and D, so those are no good. And then looking at our L is equal to 1, that crosses out E because L is equal to 2, and A because L is equal to 0. So then looking ML equals negative 1, that's a valid electron. And then MS positive 1/2, that's a valid number. So then the answer in this case would be C. Which element has the following electron configuration? So in this case, I'm sure you guys have briefly covered condensed notation. So essentially how this works is you look at the noble gas in the brackets as your starting point. So we're starting here, it says krypton. So we start at krypton, and then we're counting down the periodic table from that. So krypton, you go across the table. So this is our 5s2, 5s1, 2. And then next is, remember, this is D, so we subtract 1. So instead of 5D, it's actually 4D. So 4D10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we're back to 5 because you don't subtract 1 for P. So then 5p4, so that's 1, 2, 3, 4. So that corresponds to... Is that tellurium? I can never remember.
Technetium or something like that?
No, technetium is 43.
Oh, never mind. TE, let's see.
Oh yeah, it corresponds to TE. But
tellurium. Yeah, you're right.
I don't think you need to actually know the name, but yeah.
Correct.
So that would be
Richard.
the answer for that one. So which of the following orbitals cannot/does not exist? So
Fun.
this one is looking at our options here. So 6s, that definitely can't exist. It's right there. So that's good. So 3p definitely can't exist. That is right in this group here. So that's good. The one that's tripping you up is 2d. So remember, D starts at the 4th row and is always -1 from its actual row number. So D starts at the 3rd level. So there can't be a 2D orbital. 5G, you guys don't really have to worry about G orbitals, so don't worry about that. And then 7F is essentially, F is similar to D when you start dealing with it here, but you subtract 2 instead of 1. So a 7F orbital would be possible, but it's essentially going way off the table. I mean, theoretically, if we're in like a sci-fi world where you can make like an additional 4 rows of elements, yes, you could have a 7F. So it is theoretically possible, but there is no way in day-to-day life you're going to run into it. So, yeah, 2D would be your answer in that case. Which of the following statements for a group 7A element is true? So if you looked at your table here, you'd see that 7A are these halogens here. So reaction with a group of 1A alkali metals, so that'd be these guys here, yields a compound with the formula NX2. So these guys, these group 1 metals, always like to have a charge of +1. And halogens always like to have a charge of -1. So that would be MX, not MX2. So that doesn't work. So the second question is reaction with a group 2A alkaline metal. So that's this group here. Yields a compound with a formula E2X. So these guys like to be +2. So in that case, it would actually be EX2. So C is the correct answer, is these guys like to have a charge of -1 to look like a noble gas. And D is wrong because they don't have -2. Element X is relatively inert and does not interact with other elements. So that is true of noble gases. So that would be 1 row over, corresponding to the neon, argon, krypton, xenon, and radon, etc. So, what is the wavelength of an electron that is moving at a velocity of 680 meters per second? Okay, so in order to do these questions, you use the de Broglie equation. So I just put that there. So the wavelength in meters is equal to the velocity, or is equal to Planck's constant over the mass times the velocity. So we'll essentially just plug that into this equation. So Planck's constant is 6.626 times 10 to the -34th. What are the units on Planck's constant again?
Oh gosh. Oh boy. H, Planck's constant in joules per hertz is that.
Joules
what
per
you
hertz. Okay.
That's on your screen. I think that's right, yeah.
And then, man, I don't remember the mass of an electron. It's something times 10 to the -19th.
Oh boy. Why do I know that? Why don't I know that? Mass of electron.
You're the inorganic one.
It's,
I thought you would know.
Oh boy, that's funny. Why doesn't that just come up when I Google it? Gosh. Mass of an electron in kilograms. Okay. 9.109 times 10 to the -31 kilograms.
Negative
So
31
then you'd
kilograms.
have to
Uh,
mass of an electron in it should be in kilograms. Yeah,
Yeah.
I was thinking we needed to convert that. Yep.
No, we want all these in standard SI units, so that's good. Kilograms. And then the last is the velocity in meters per second, so we don't have to do any conversions there. So 680 meters per second. So hertz is kind of seconds inverse, so that will cancel. And then, yeah, kilograms per meters kind of cancels with joules, so you'll be left with a wavelength in meters.
Yep.
And that is...
Oh gosh, sorry. I'm thinking about the joules too much. That's gonna be your answer, I'm pretty sure, but...
Yeah. Times 10 to the negative 6 meters, which kind of makes sense because an electron that's moving that slow is going to have a very small wavelength.
That's right.
Okay, moving on to the next question. Arrange the following isoelectronic ions in order of increasing radius. So isoelectronic essentially means they have the same number of valence electrons. So what's going to determine their radius is their number of protons. So remember, there's the relationship is the protons in the middle of the atom are essentially trying to pull the electrons in. Well, the electrons on the outside are trying to repel each other, which are keeping them out. So since the number of electrons is the same, we look at the number of protons. So whatever has the most protons will have the greatest force trying to pull the electrons in and would therefore have the smallest radius. So just looking here, calcium is number 20, so that's going to have 20 protons. And then sulfur is going to have 16 protons. And then, what was the last one? Chlorine is going to have 17 protons. So calcium has 20 protons. So that means it's going to have a lot of protons trying to pull in the same amount of electrons compared to the other two. So it would be the smallest. Likewise, sulfur has the fewest protons trying to pull the electrons in. So therefore, it would be the largest out of the bunch. So that would give you your answer of A. So, 33. For the anion tellurium 2-, which of the following statements is correct? It is isoelectronic with krypton. So isoelectronic means that same amount of electrons. So tellurium 2- would move 2 over, so it would look like xenon, not krypton. So A would be wrong. So it will combine with Al3+ to form Al2Te3-. So if you look at these charges here, 2 times 3+ would be 6 for the aluminum, whereas -2 times 3 of those would be -6. So this is a compound that would form, so that would be true. So Te has 52 electrons. So looking at tellurium here, it normally, because its atomic number is 52, would have 52 electrons in its ground state. However, the catch-22 here is that it's in a 2- charge. So it's actually gained 2 more electrons. So it actually, in this case, would have 52 plus 2, or 54 electrons. So C would be incorrect as well. And then D and E are just combinations of those, so those don't matter. So which of the following descriptions is correct given these electronegativity values? So remember, for electronegativity, that less than 0.4 is just covalent. And then greater than 0.4, or no, wait, whoops. Less than 0.04 is covalent, greater than 0.4, and I believe it's less than 1.5 is polar, and then greater than 1.5 is ionic. So you essentially want to look at the numbers and subtract the difference between the two. So this first one here, cesium is 0.8 and fluorine is 4.0. So that'd be a difference of roughly 3.2. So that is definitely going to be ionic. So that one is not polar covalent, so that's wrong. So Cl2, that is going to essentially be 3 minus 3, so that's going to be a difference of 0. So that would be nonpolar, so it's definitely not ionic, so that's wrong. So NO is listed as nonpolar, so nitrogen is 3.0 minus 3.5. So that is a difference of 0.5. So that's above our 0.4 threshold, so that would be a polar bond. So that one's wrong. So then HCl, which is our answer, is polar covalent. So if we look here, chlorine is 3.0 minus hydrogen, which is 2.1. And that gives us a difference of 0.9, which is within the threshold for a polar covalent bond. So that one is correct. And then our last one, just to prove it's incorrect, BrCl is 2.8 and 3.0, so that's a difference of 0.2, so that would be considered a non-polar bond. So polar covalent would be the inaccurate term for it, so that means your answer is D. So 35, what number is nonpolar? Okay, anything with an electronegativity difference below 0.4 is considered nonpolar. So if we looked at E here, that was 2.8 minus 3.0 for the chlorine. That would be a 0.2 difference, so that would be considered nonpolar. So if you just look at the difference in these numbers, anything that's 0.4 or higher is considered polar. So does that clear it up for you, Vivian? Yeah, covalent is nonpolar.
Right, yeah.
Covalent just specifies the type of bond. So covalent bonds can be nonpolar or polar. It depends on the electronegativity difference between the two atoms. So the difference between covalent and, I just want to make sure people don't get confused by this. So covalent essentially means that the two atoms are actually sharing electrons, whereas ionic means that one atom actually steals the electrons and doesn't share them with the other one and causes charges. So in that case, the two atoms are called together by their difference in charges. So covalent is essentially two kids that know how to share, whereas ionic is the bully in the corner who doesn't want to share his toys. For lack of a better analogy I can think of off the top of my head.
Right, but then covalent can be both polar covalent and then non-polar covalent.
Yeah, exactly. So the sharing, the level of sharing kind of depends. Because one kid might want to just hold on to it for a little bit longer compared to the other one. So in that case, that's considered a polar covalent bond. Whereas when they're all happy and sharing them equally, or relatively equally, that's when it's called a non-polar covalent bond.
Right.
All right. What is the formal charge on phosphorus in PCl5? So remember that chlorine is our halogen, so that's in the furthest right with the exception of the noble gases. So those are always going to have a charge of -1. So if we look here, remember I always like to do this as a math equation. So we have our phosphorus, oh, why'd that get erased? Plus 5 chlorines, which always have a charge of -1, equal our overall charge. So this overall molecule doesn't have a listed charge. So in that case, our overall charge would be 0. So then we just solve the equation. P minus 5 equals 0. So then P equals 5. So then the formal charge on phosphorus in this case would be plus. Why is it circled as 0?
No, I think they made a mistake in this question.
Yeah,
They were probably asking what the formal charge for the molecule is, but
yeah, the formal charge for the molecule is 0. The formal charge on phosphorus would be 5.
that's right.
So I don't know why they circled 0. So that's just a bad
Typo.
yeah. So given the bond enthalpies below, calculate the enthalpy change for the following chemical reaction. So NH3 plus Cl2 goes to NH2Cl plus HCl. So it's essentially in this case, it's the heat of bonds broken minus the heat of bonds forming.
Right.
So we did a question similar to this in last week. So we essentially want to look at each of these molecules. So NH3 is going to look something like, this. So we're going to have 3 NH bonds in it. So an NH bond has a total of 389 kilojoules per mole, and since we have 3 of those, that takes care of the first one. Now we want to look at the Cl2 here. So a Cl-Cl bond has a 243 kilojoules per mole, and there's only going to be 1 of those. So this is our bonds broken.
243. That equals 1,410 kilojoules.
Kilojoules. And now we want to look at our bonds forming. So, in this case, we're going to have 2 NH bonds and 1 NCl bond. So in that case, that would be 2 times 389 kilojoules. Plus 1 NCl, so that's 201 kilojoules. Plus, and then we're looking at our HCl, there's just 1 of those, plus 431 kilojoules. And this is bonds formed.
Which is 1,210.
10 kilojoules.
I'm off by 200.
So the reason we put this negative sign is because bonds forming is an exothermic event. So that's why this negative sign occurs here. So then you essentially just subtract this guy from this guy, which should give you plus 200 kilojoules.
Just a second. I think I calculated it wrong.
Oh, did you?
I should have put 1,401, which would make sense with the 1,410 kilojoules.
Kilojoules, okay.
Yeah, but
So
those will be negative. Yeah.
Yeah, negative, so then those cancel each other out, so then your net difference would be 0 kilojoules.
Yep,
Which
exactly.
would give you your answer of E.
Perfect. Yes.
37. A molecule has a formula of Ml2. Atom M is the central atom, and the MLM, that's a wordful, bond angle is 117 degrees. What are the most likely electron groups? So in this case, thankfully you guys get to look at your table. So judging by the fact that it is 117 degrees, that means roughly, if it was all equivalent groups, you would get something that would be 120 degrees like this. So it would be M, L, L, L. But the big caveat here that's causing these angles not to be 120 degrees is one of these is actually going to be a lone electron pair. So a lone electron pair is more repulsive than the 2 bonded groups. So these angles are going to be bigger, and then it pushes these 2 guys closer together. So instead of normally being 120, it's actually 117 degrees in this case. So then your answer would be 2 bonds and 1 lone pair of electrons that's causing that. So how you would figure something out like that out on your exam was you would want to look at your table of electron and molecular configurations and find an angle that is similar to this one on your table. Okay, so that's that one. How many equivalent resonance structures does the ion NO3- have? So, we're going to have to draw this guy out. So remember, the first step is count how many valence electrons we have to work with. So nitrogen normally has 5 valence electrons, plus we have 3 oxygens, each having normally 6 electrons, plus we have a negative charge, so we get 1 more. So that gives us 5, 18, 19, 24 valence electrons. So then in the center, we'll put the least electronegative, so that's N. And then we put a single bond to each O. And then we fill in the octets. 1, 2, 3, 4, 5, 6. So if we're looking here, this is our 24 valence electrons. So now essentially what we want to do is try and minimize formal charges. So each of these oxygens, remember to calculate a formal charge, you do the normal number of valence electrons oxygen has, so that'd be 6, minus the number of lone electrons, so that is 6, minus the number of pairs, or bonds, sorry, so that would be -1. So then each oxygen is going to have a formal charge of -1. And then the nitrogen, likewise, normally has 5, minus 0 lone electrons, minus 1, 2, 3 bonds. So that's going to have a charge of +2. So in order to minimize formal charges, what we'll do is we'll take one lone pair of electrons and convert that to a bond for the nitrogen. So this completes the octet for nitrogen, and instead of having a +2 charge now, it'll have +1, so that's better. Each of these will still be -1, and then this one will have a charge of 0. So there's not much else you can do to minimize the formal charges on that structure. But what this question is asking is how many resonance structures this guy can have. So this double bond here doesn't necessarily always have to correspond to this oxygen. So it could be on this oxygen, on the bottom one, or it could be on the one in the top left here. Each of these structures is equally valid, and the actual structure will be a hybrid of the 3. So since there's 3 possible resonance structures, and they're all equivalent, that would mean your answer would be C. Which of the following molecules has a net dipole moment? Can't you add another double bond? So in that case, I feel the table would be handy here. So remember that in order to add another double bond, that would violate the octet rule. And remember that stuff in group 2, it's only stuff in group 3 or lower that can accommodate more than 8 electrons in its outer shell. So nitrogen here is in the second row. So we cannot break the rule that nitrogen can have more than 8 in its shell. So if we can't break that rule, each of these has 8, and there's nothing we can do to increase it. So yes, if this was something in the same row that was like a column lower that could accommodate more electrons, yes, definitely we could minimize the charges on it. But unfortunately, there's nothing we can do to overcome that octet rule for nitrogen.
For sure, but right now this molecule does have a charge of -1 because the positive and minus on a nitrogen and one of the oxygens cancel out. So it has an overall charge of -1.
Yeah. You want to ideally get the formal charges to 0, but that isn't always an option.
Mm-hmm.
Sometimes it gets ugly.
Like Richard said. If it was phosphorus, though, I think you could do what you're saying and have it with 5 bonds.
If you replace the nitrogen with phosphorus, that would look something like this. I don't know how many phosphorus could actually accommodate, but it would probably end up looking something like this.
Probably. Yeah.
So then you'd have your overall charge of -1 on the oxygen, which there's not much you can do to get rid of that. And then, yes, the phosphorus would now have a formal charge of 0. But
Right.
it's the fact that nitrogen is in the second row and we can't break that octet rule that's causing the issue there. But there's nothing we can do about that.
Yeah. Good question, though.
Yeah. Which of the following molecules has a net dipole moment? So this is essentially going to be looking at the 3D geometry of the molecule. So looking at this first one here, boron would be in the middle, flanked by 3 fluorine atoms. So if you remember, boron is in this group here that doesn't mind having a valence shell of just 6 electrons, and each of the fluorines are going to be filled with their 8, so that's fine. So the Lewis structure would look something like this. And if you looked on your table, you would see that each of these guys is 120 degrees apart. But essentially what I like to imagine this as is essentially a tug of war. So these are all in the same plane, and fluorine is going to be far more electronegative than boron. So fluorine is pulling the electrons away from boron in 3 opposite directions, and they are essentially canceling each other out, so there is no dipole moment, even though the bonds are polar. So they're going equal in opposite directions in equal magnitude. So that'll kind of make sense as we keep going through these examples. So the next one is BeCl2. Goodness, where's beryllium?
That's right by lithium.
Oh, okay. So that, in this case, would actually be a salt, but it would look something like this, with the chlorine pulling the electrons this way, and then the chlorine pulling the electrons this way. So it's kind of a classic tug-of-war scenario, where it's trying to pull this way, and it's trying to pull that way, so the rope doesn't actually go anywhere. So there is no dipole moment in this case either. And then in the case of CO2, that would look something like this. So that would be the exact same thing. The oxygens are trying to pull the electrons to themselves, but there's no net change because they're in opposite directions. And then CH4, a carbon-hydrogen bond is not considered polar, so this one would not even have a dipole moment. So that one's not a big concern. So NH3, if you drew it out, it would look something like this. So you're going to have nitrogen, the lone pair of electrons, with a hydrogen here, a hydrogen here, hydrogen here. So it's kind of hard to visualize, but this lone pair of electrons would be at the top here, and then 3-dimensionally, each of these hydrogens would be like a 3-sided pyramid kind of pointing down. So nitrogen is more electronegative than hydrogen, so nitrogen is going to be pulling all of these hydrogen atoms' electrons towards itself, which is going to give it kind of a negative dipole moment over here. And all these hydrogens are pulling, but they're not being canceled out because they're not in opposite directions, so it will have a positive moment over here. So then the answer as to which one has the dipole moment would be this guy. So it's kind of difficult, but you kind of have to visualize the Lewis structures and visualize the 3D shape of the molecule as to where the atoms are trying to pull the electrons in it. Because you can have polar bonds, but it doesn't necessarily mean that the molecule overall is polar, because those bonds might be canceling out other bonds. What intermolecular force is the most important between CH3Cl molecules in a pure sample of a compound in the liquid phase? So remember, our molecule is going to look something like this. Oh wow, that is a very spaced out drawing. But anyway, so remember our intermolecular forces is we can have dispersion forces. Those are present in every type of molecule. So that's definitely going to be one that we have. Next is dipole-dipole. And that's dependent upon if the molecule has a polar, or if the molecule is polar or not. So in this case, these CH bonds aren't really going to matter, but this chlorine is more electronegative than the carbon, so it's going to be trying to pull electrons towards itself, giving it a partial negative charge over here. So that means it is a polar molecule, so dipole-dipole is going to exist. So the next one on the totem pole that you have to look at is hydrogen bonding. So that's when we have a hydrogen attached to an oxygen, a nitrogen, or a fluorine, which we don't. So then that means that the highest one we have to deal with is just dipole-dipole. So then, in that case, our answer would be C. Which of the following compounds has the highest boiling point? So this is the same concept. We want to look at the intermolecular forces for each. So if we just look at our first guy here, our CH4, there is no polar bonds. There is no hydrogen bonding. So the only thing that's keeping this guy together is just dispersion forces. And those dispersion forces themselves aren't even going to be very strong because it's a small molecule. So that one would definitely have the lowest boiling point. So then if we looked at D here, that's the exact same molecule as in the previous question. So that one had dipole-dipole. So that one would have a higher boiling point than dispersion, but unfortunately, there are ones that are stronger. And then if we look at E here, that would just look like this guy. So this would be a non-polar bond because there's two nitrogens. And so that would just have dispersion forces as well. So that leaves our two main candidates are lithium fluoride and H2O. So water looks like this. So it would have dispersion forces, and the oxygen would pull the hydrogen's electrons towards itself to have a dipole here. But the main notable thing is we have a hydrogen bonded to an oxygen. So that means this guy has hydrogen bonding intermolecular forces. So that gives it an exceptionally high boiling point. But there is one stronger one than hydrogen bonding intermolecular forces, and that is ionic forces, which you find usually in in a compound that contains a metal and a non-metal with a huge electronegativity charge. So in the case of lithium fluoride, you're dealing with lithium, which is a highly electropositive element, loves to give up its electrons, and fluorine, the most electronegative element in the table. This one is definitely going to be ionic. And since ionic is the highest on the totem pole of ionic, then hydrogen bonding, then dipole-dipole, then dispersion, that means that lithium fluoride is going to have the highest boiling point. Okay, number 42. Ethanol has a heat of fusion of 5.01 kilojoules per mole. How much heat is required to melt 137 grams of ethanol? So a little roadmap for this guy wouldn't hurt. So we're starting off with a mass of ethanol. Oh dear, what just happened?
Ah!
What on earth just happened? How do I zoom out? Oh boy. Okay, there we go. Oh no. Okay, sorry.
There it is.
So we're starting with a mass of ethanol. And then we want to end with a heat. So we need to figure out how we want to get from point A to point B. So here is looking, if we have a mass of ethanol, we can go to moles of ethanol because we have its chemical formula. Yay, we get to calculate another formula mass. And then once we have moles of ethanol, because we have a heat of fusion, we can go directly to heat. So to go from a mass to moles of ethanol, we're going to need to calculate that. So we got 2 times 12.011 grams per mole for the carbon. plus 6 times 1.00794 for the hydrogen, plus 15.9994 for the oxygen. I recall that comes out to like 50?
46.
46?
Yeah. 46.0694.
694 grams per mole. Next, we can go to mass. So, they said we had 137 grams, and then our conversion is 46.0694 grams per mole. Whoops. I'm fudging up my units here. Grams per 1 mole. And then that would be
2.97377. Don't know if you need all those, but
I'll just write them down. So then in order to calculate the heat, we have 2.97377 moles of ethanol. And then the heat of fusion to melt it requires 5.01 kilojoules of heat per 1 mole of ethanol. So that should come out to roughly 15-ish.
Yep, 14.9.
14.9 kilojoules. Which
Yes.
means our answer would be E. And I believe we just finished the multiple choice section.
Indeed.
Woo! Okay, so do you guys want to keep going and cover or at least part of the written answer section?
Oh, okay. Well, another thing we could do, Richard, is do these on our own, and then we could post them or provide them.
I was gonna say, like, I can do these questions in a video and then just upload it to the same place I will upload the tutorial stuff for tonight. So
Yeah, perfect.
would that be okay with everyone? Because I do believe I have to help my parents move tonight as well, so.
Okay, yeah. Good.
So anyway, I hope this helped everyone. I hope it helped, relieve a little bit of the stress and clarified some things.
I hope so too, yeah. I think my big tip would be to ask Dr. Ellis or Pearson which information will be provided to you, and then make yourself a really easy, like basically pretend that you were just bringing in one sheet to the exam and make like a cheat sheet equivalent. So like I would have all those tables that tell you like the acid names, and I would put that on like the same sort of page.
Want,
and
acid names, just naming convention for molecules in general.
Yeah, and then ask, like, are we going to be provided with, the equation for, like, PV equals nRT, or, like, the R values with their units, or then have, like, the equivalent of atmosphere to torr conversions, or, like, atmosphere to millimeter mercury conversions, or, like, those kind of things.
Definitely an important one. Get yourself I forget which page I put it on. Get yourself something
Periodic
that looks
table?
like
Oh.
this. Something
Yeah,
that
exactly.
includes your electron groups, your bonding groups, your lone pairs, and then that just allows you to determine your geometry and your bond angles.
Yeah, those are perfect.
Yeah,
and then I would get a periodic table, and I would mark it up with, like, this is the S block, this is the P block, this is, the 3D, because it changes, so make it really, really easy for yourself.
Yeah.
Yeah, but yeah, this would be awesome to have too.
Yeah, so I just searched, like, molecular geometry table online. It's pretty easy to find.
For sure.
But yeah, just essentially, like, put put together a cheat sheet for yourselves. It'll just make your lives so much easier.
And that's like valid studying too. Like, it's awesome.
Now, I think I'm going to. Do you guys have
All right,
like?
well, thank
any,
you guys for coming. This was awesome.
Do you guys have any like last minute questions? I remember somebody had a question.
Oh yeah, what is that one? Thanks. Good luck with your guys' tests too.
Yes, good luck on your guys' tests.
Oh boy.
Okay, it popped in here. Let me see.
Cyclohexanone and cyclohexanol.
So are they asking what the
Like what
forces are between the two of them?
like what the intermolecular forces are? I can't figure out. Oh, that's okay. Yeah, I guess it doesn't say like what exactly the is. Looks like they're asking for what those forces are in the molecule. Well, everything has London dispersion.
Yeah. I feel like they're asking in a mixture between those two molecules what would the forces between the two be.
Ah.
But yeah, don't worry about the diagrams because like I know what all those molecules look like, so that's no big issue.
Yeah, that's fine. We can derive those. Oh.
Have any studying tips? I'd say just honestly keep practicing all the. Yeah, as bad as it sounds, practice makes perfect for this course. There is a lot of material to cover, but honestly, how I study for other courses is I just kind of amalgamate all my notes into one document and just kind of read it through and relate the concepts to each other.
Yeah, I would do a lot of questions and a lot of examples, and I would do them without consulting the answer at all. Like I would just not even have the answer and do like a practice final or something completely through, and then I would look at the answer.
Yeah. And I have
because if you have it with you, then it's just like what we did right now. We kind of went through them and we knew what the answer was. That's not really helping you, right? So I would just have a blank document or whatever, and then at the very, very end, I would go and look what exactly the answers were and what I got wrong.
So I've tutored this course in the past, and I found something that has really helped people is what I call a roadmap. So it's essentially like kind of a methodology you use to figure out how to solve the questions. Because a lot of this course really boils down to essentially is converting one thing to another and figuring out what formula or conversion ratio or something you need to convert from that one thing to that other thing. So I was doing it throughout when we were doing the exam is we had the question once, whatever it is, X. And then we start with Y. So usually, more often than not, you can't go directly from X to Y. But if you look at the question, you can usually see, okay, there's a way I can go from Y to Y2, which is something different that is closer to what I want as my final answer. And then I can go from that thing to another thing, and then from that thing to another thing. You just essentially break it down piecewise and figure out what you need to convert from one thing to another to get you to something that can get you to your final thing you're looking for. It obviously doesn't cover every type of question in this course, but it does cover a surprising amount of them.
Exactly. Another thing I find really helpful is going into the syllabus, or if they give you like a course outline or something with like basically bullet points of what you need to do and being like, do I understand what this relationship is? Like they'll have, you need to know the de Broglie relationship, or like an ideal gas equation or whatever, and then I would kind of go through and check things off, like, okay, yes, this is what I need to work on. Okay, let's work on this section.
And then
Yeah,
remember,
I
like,
really like that.
your periodic trends for, like, electronegativity, ionization energy, atomic size, stuff like that. But yeah, honestly, how I studied for it was I just went through every question I could sink my teeth into. And also spent a lot of time making flashcards, memorizing the molecular geometry shapes, but thankfully for you guys, it's open book, so you don't really have to worry about that part.
Exactly. Like all the acids we had to remember and
Yeah.
all those like ions and stuff, yeah. And that's good.
Yeah. So I will finish this recording and then I will upload it later tonight, and I will also do a recorded section for the written part of the exam, and I will upload that on the same source, whether that's YouTube or I'm not sure which source it'll be yet, but I will let your professors know, and then I will either get them to tell you or I will post it in the Discord here, so stay tuned.
Awesome. Any other questions for us before we head her? I guess we didn't really address the question that I think it's Mika posted.
Yeah, I am so sorry.
But I guess we didn't really have the question. Like, was it a mixture of the two, or like, are we just comparing the two?
Yeah, I'm not sure.
Oops.
Okay, which intermolecular forces do the following pairs of molecules experience if mixed together? Okay. Okay, that's easy enough.
Yeah. So
So-
cyclohexanone, that's a ketone, right?
Yeah, that would look something like this.
Yep. And then the cyclohexanol, that'd be just an alcohol. So then that one, everything's going to have London dispersion.
Yeah. So this one is going to have hydrogen bonding because it has the OH. So that one definitely be there. There's no charges, so ion-induced dipole is not there. And
Right.
since this oxygen is polar, making that molecule polar, you're also going to have dipole-dipole. So the first
Right.
one would be dispersion, dipole-dipole, and hydrogen bonding.
Right. And then I think if like hexanone was on its own, I don't think that would have hydrogen bonding if it was just like the pure compound.
No.
But because it's in a mix with something that has a hydrogen on, like an oxygen or a nitrogen, then it will be. So hexanone would be a hydrogen bond acceptor, but then the alcohol would be the hydrogen donor, or hydrogen bond donor.
Yeah.
Yeah.
So then our second one, we're dealing with cyclohexane and cyclopentane. So we're going to have that guy and that guy with all the hydrogens filled in.
Right.
So since we don't have anything that's not a carbon or a hydrogen, there's going to be no dipole-dipole forces. There's no
Right.
hydrogen bonding. So the only thing is going to be dispersion, since that's present in everything.
Yes.
Then the last one is
Cyclohexanol and water.
So cyclohexanol. So that one looks like that. And then we have water. So we have the oxygen bonded to the hydrogen in both of these cases. So we're definitely going to have hydrogen-hydrogen bonding. And then this one's going to be polar here. And this one will likewise be polar. So we'll also have dipole-dipole. And we always have dispersion. But there's no actual charges, so there's no ion-induced dipole.
Right.
So those would be your 3 for the third one there.
Does hydrogen bonding mean dipole? Dipole is always there. I think so. It's kind of hard to say. Well, dispersion, yeah.
I mean, I know dispersion is always there, but what if you had, like, a diol? I'm trying to think here.
Of when you wouldn't have.
Because what if you had something like this?
Right. Yeah.
So that would have hydrogen bonding, but
No
because these two
dipole.
would cancel each other out, there would be no dipole. So it would be possible to have hydrogen bonding without dipole.
Right.
So the first one with the hydrogen and the O and the OH had a hydrogen bond. Or is the hydrogen bond just present with the OH? So in that case, this one has the hydrogen bond present with the OH. So there would be hydrogen bonding in between these two. But there's also a strong attractive force because this hydrogen bonding essentially means that there is an exceptionally really negative part of the molecule that's electron rich. Because hydrogen is really good at giving up its electrons. So in this case, there's kind of a hydrogen bond attraction between this part of the molecule here, and it's going to be attracted to that part of the molecule there.
So yeah, I think the hydrogen bonding is actually intermolecular, so it's between two different molecules in solution. So it's that hydrogen being attracted to like a lone pair. So a lone pair taking some of that hydrogen away.
Yep, sorry.
So whether that lone pair is on like the oxygen of the OH or the oxygen of the ketone, that doesn't matter.
So yes, this hydrogen is going to be attracted to these lone pairs here.
That's right, yeah.
Right? Yeah.
So that hydrogen bond is actually like the hydrogen and one of those lone pairs in another molecule. So that's why like the alcohol can be a hydrogen donor and acceptor, but the ketone can only be the hydrogen bond acceptor.
Yeah.
Yeah, so I think there's a word for it, like hydrogen bond acceptors and then hydrogen bond donors. But then if they're both, do you know that word? It's like water, obviously. Can be like hydrogen bond acceptor and donor. Probably
I'm trying
something.
to remember what that word is.
Something like, yeah.
But yeah, like
in the something
case,
ambi.
In the case of the second one here, this hydrogen is going to be attracted to the lone pairs on the water, and then this hydrogen is going to be attracted to the lone pairs that I did not draw in on this alcohol.
Yeah, exactly. So yeah, I think a classic thing, professors will point to like the hydrogen-oxygen bond, that covalent bond, and be like, that's not the hydrogen bond. The hydrogen bond is between two different molecules. If that makes sense. That's good. Thanks for coming.
Yeah, thank you for coming, everyone. I will finish that second part of the video tonight, and I will get everything uploaded for tomorrow. Good luck on your final exams.
Yeah, good luck. You're welcome.
You're welcome.
Good luck on your final. Any other questions?
I think that's all of them.
Awesome. Okay, well, let me know if you want me to help
Hang
you out
on.
with
I'm
those.
getting a phone call, Grace. Sorry.
That's okay.